our model will be performative on new data that we see, right? So the real risk of that's apparent in this exercise is that, we'll build a model that's so highly attuned to the data that it's looking at that it won't be of any use when we look at new data, right? So if we've collected a bunch of data on loan applicants, we really don't want to sort of predict only those loan applicants really well. We want to make sure that we can predict new applicants, right? So that we can use this data in the real world. So, but our limitation is we only have one data set, and this is only like one realized sample of the world, right? Um, so, you know, we talked about our performance metrics like AUC, root mean squared error. So these are estimates, right? But like resampling is how we get better estimates, not just better estimates for our training data, but for new data we might see. So in finance, you care about model performance matters because we decisions have a cost, right? So in credit risk, right, false positives, right? These are people who we thought were going to default but didn't default, right? So those really don't matter because that's more of a missed opportunity. But false negatives is the real sort of crux there, right? Where we don't want to lend people money thinking they're good customers and they turn out to be bad customers. That's called type 2 error, right? So we really care about type 2 error. But, we also care about other things, if we're doing risk management, asymmetric losses. And then we also care, this is where the overfitting sort of conundrum really kicks in, like stability matters, right? So we care about both the level and stability of the performance. We want a performative model that's going to perform for a long time into the future. And I will say that, like, in my job, so my job is to build credit stress testing models that are used at my company. We have a whole oversight group called Model Risk Management, and they sort of come out with like rules around, we need to model the performance of our monitor the performance of our model and demonstrate that it keeps performing over time. And if we see a degradation in the performance, then we have a discussion about like building, rebuilding the model. So the thing, and we'll see this, we have an example tonight when we're doing our coding, and we'll do a live coding session a bit later. But like, if we do we talked about this train test split, right? That's kind of the minimum, right? We definitely want to have a holdout data set to evaluate our model performance. But even a single train test split is a roll of the dice. It's a random thing, right? So we will get an estimate of the model performance, such as, root mean squared error or AUC, but like that could be a noisy estimate, right? So, um, and it's just due to randomness. So we do a random split, even if it's a stratified split, we'll get different data in there. And we'll get different data in the training and test sample depending on that roll of the dice. We do that set seed thing. And if we were to repeat that over and over, we would see that there's noise there. And if we only do it once, we have no idea about that sort of the variance that's present in that noisy estimate. And the other thing is like if we're talking train test split, the real intention of that test data set is like a final exam. We're gonna put that aside and keep it in a locked place, right, where we don't touch it until we've done work to sort of finalize our model. And we may find, we may end up like comparing several different models, or we may need to do things like we'll talk about this idea of what a hyperparameter is, but there may be decisions we need to make along the way that we'll want to try out different values or different sort of choices to make that we want to sort of have an idea of whether we made the right choice or not, right? So what we can't do or what we shouldn't do is repeatedly look at that test data set. And even if we don't intend that to happen, we may find that the idea is like you get a leakage of information from the test set, right? So we don't want that. We don't want the test set influencing our model development, because if it once that starts happening, we could be at risk of that sort of dreaded overfitting uh, situation. So I've got a question here, thought experiment. Two analysts do the same thing, right? And analyst A gets an AUC of 96%, which is good. And analyst B gets an AUC of 92%, which is also good, but not as good as 96%. So they both use the same code and the same model. They had just had different splits, right? So maybe it was maybe they forgot to set the seed, right? So if I run the same code on two different machines, forget to set my seed, I'm going to get different results. So the question is like, what is the true performance, or did anyone do any, is one better versus the other? And if I had some sort of foresight here, oh, that's kind of weird. You know, I'm not going to do it on the fly. I guess I could do polling. Right. Yeah. So A, B, neither. Okay. So is that going to work? Do you guys see that? Can you? Okay. So people are responding here. We'll see if we can get a couple of maybe a couple more. Okay. Oh, if we get one more, we'll have full participation here. All right, so we'll keep it there. So two people said A, one person said B, and four people said neither. So let's return to our example here. So the answer is, they both did the same thing. I mean, these are two estimates of the same thing, right? So they're noisy estimates. So even though 96 is better than 92 on paper, it's statistically they're the same thing. Like we would see if we repeated this exercise 100 times, we would see a distribution of outcomes, and it's very likely that both of these results would be considered statistically the same outcome, right? So I would imagine that the true performance is probably somewhere either between these, or even like if it's a very noisy thing that could be kind of far away from these things, right? So that's why if we do if we do the right thing and apply some of these concepts here that we're going to be talking about, we'll not only sort of have a better estimate of the true performance, but we'll also have an estimate of like how noisy that performance is. So when I talk about resampling, the concept is, rather than having one held out data set, right, we're going to replace this. We're going to use different techniques to have many plausible held out sets, right? So, we might be looking at 5 or 10, or we could even be doing it like repeated cross validation where we do, 5 or 10 repeated 5 or 10 times, right? So we could do this a lot of times, and it's by doing these repeated approaches, we're able to compute performance on each. And then our summary is going to be sort of less, rather than a single number, this is called a point estimate. We're going to have an idea of what the distribution of this noisy estimate is. So we'll have a mean and then a spread, right? So that's a much more informative idea of how our model's performing. So just to sort of revisit here, and because we will be talking about a thing called hyperparameters. So a parameter, right, would be something like, we looked at those those beta values in a logistic regression or a linear regression. But if you remember, like that was something that like we have an algorithm and a supporting function that we could use to fit that model, and that was learned from data, right? So it's directly from data. So we run, in RStudio, if we were to run over here, well, I can't do it right now, but run that LM or DLM function that we were talking about a couple of weeks ago. That would be something that the data really directly informed us of what those root coefficients were. Performance estimate is computed from predictions, right? So we're always, while we do care about in-sample performance, we get the summary for our linear regression. We saw, a summary of the errors, terms in there. That's kind of an indication of how well our model fit the data, how close we were to the actual values we were trying to predict. But we really care mostly about looking at predictions on new data, right? So the AUC on some holdout data set, right, is what we care about. And resampling is repeated fitting and evaluation using a structured reuse of the data. So we didn't really talk here about I thought I had put another bullet here. Maybe if I repost these slides, I'll add it. And there's another concept here that we're going to introduce, and I think I probably have a slide on it later, called a hyperparameter, right? So that's different than a parameter. It's more of like a choice we need to make as we build our model, right? So we'll be looking at an algorithm tonight called k-nearest neighbors, which is sort of a non-parametric approach, right? You don't estimate any parameters from this k-nearest neighbors approach, but you do need to choose a hyperparameter, and that's that number k. How many neighbors do I want to consider, right? So that's something that like you need to tell the algorithm what your choice is, and it'll produce a model. But it's not something that's directly learned from the data. You need to kind of provide that up front. And we'll talk about how resampling helps with that. Right. So tonight we're going to talk about some of the different approaches that we use. And I will say that like we are going to spend most of our time on k-fold cross-validation. Right. So these are kind of like they're not ranked in any particular order, but we'll talk about like the idea of like in addition to a trained test split, we can then further split our training data into to create a validation test set. If we have enough data, that's kind of dependent on sort of how much data we have to spend on this type of thing. We will look at an approach called leave one out cross-validation, which is kind of computationally intensive. So this one is used sometimes. Some algorithms kind of you get this for free a little bit, so it's really sometimes help a question of what algorithm are we using. But we're going to talk a lot tonight about k-fold cross-validation, which is a little different than k-nearest neighbors. So don't get hung up on that k. But this does indicate like how many of a thing you're going to choose, right? So this is another thing. Now this k for the k-fold cross-validation is not really a hyperparameter either. I just was talking about hyperparameters, but this is not something you would tune. It's kind of just more of like we're going to pick a number, and usually people pick a number like 5 or 10 and they're done with it. They don't really belabor that choice too much. So we'll focus a lot on this one, but we will talk about two more. Bootstrap is sometimes quite popular. So this is one that we'll sort of just touch on a little bit, but not too uh, we won't lean into it too much, but I'll give you an understanding of what it means. And then if we're talking about particularly time series modeling, which is something that comes up quite frequently in finance, you might be thinking about doing like more of a rolling window or an expanding window time series type of thing. So that's where your holdout sample would be a particular point in time. So you might do something like, I'm going to fit my data on everything up through the end of 2024, and then I'm going to hold out 2025 and the couple months of 2026 that we've seen so far, and predict on that data and see how well my model performs. Right, so that's usually a good way to go for particularly for time series where you know that time is kind of an important dimension that you're worried about. Um, so okay, so we'll kind of go quickly through some of these just so you kind of have a sense of what the what it means, but we're not really going to linger too long here, right? So this is the first approach. We could just take this a validation set. We could do another split on our training data and create a validation set, right? So the first thing we do is we split data into train and test. Oh, I guess maybe well, maybe I'm sort of misrepresented here exactly what this is. But you really do a single split of your data, whether you do train and test and then evaluate on test. That's kind of forbidden. You're supposed to keep test to the side. So I actually probably should update this slide to say train and validation. Well, split data into train and test. Further split your training data into train and validation. You fit the model on train, you evaluate on validation, and then you kind of get your add a sample, right? So this is very simple to run. And I apologize for the confusion on the slide. We're kind of adapting, a new book here, so give me apologize. Simple. It's a conceptually simple. It's fast to run, and it's good for quick sanity checks. But you're still doing a single test, so like that sort of you're not gaining any benefit from doing any sort of repeating operation to understand what you're still getting a point estimate. You're not getting a distribution of outcomes, right? And uh, if I'm trying to model rare events, right, it can be misleading. Like even that single split, I don't know exactly where the thing I care about is going to land, right? So we did talk about stratified sampling, but even then, it could be an issue. And then, it's not really particularly suitable for model selection if I'm comparing a lot of different models, or if I'm trying to sort of pick what is a good value for my hyperparameter. So that kind of is called tuning. If I'm trying to tune my hyperparameter, it's not really useful. So, you could do this, but there are better approaches to use here. Um, what makes the validation set estimates noisy? Smaller, so you have a smaller training set. So you took a portion out of your training data and you held it aside. So I've got less training data. Smaller test set. That's kind of your validation set. And when I have a class imbalance, right, where I'm trying to predict something that maybe is a rare thing, this could not be optimal. So we don't really spend a lot of time on that sort of validation approach, even though I seem to have a lot of slides on it. But we did sort of touch on rare events. So the next approach that we're not going to hang out too long on, but we kind of for completeness, if you go to the Introduction to Statistical Learning with our book, they talk about this idea of leave one out cross validation, right? So this is a case where I hold out. So let's say I have 1,000 observations. I hold out one observation, and I train my model on the other 999 observations. And I do that 1,000 times, right? So I hold one out And every time I'm training the model on the remainder, and I'm evaluating the performance uh, uh, on the one holdout, right? Uh, so I get 1,000 different measures of AUC or RMSE, and I can see how that performs. So it's appealing because I'm sort of really taking a lot of advantage of my training data. Um, so we're using almost all the observations each time. But as you can imagine, it's computationally intensive. I kind of had to fit 1,000 models, right? And it still can have high variance, right? So I still could get sort of uh, a wide variance of the performance of my model, right? So this one is, not not used too frequently, but like I said, there are some algorithms where kind of this is very, very easy to calculate, so it kind of comes for free. So sometimes leave one out cross validation is something that you'll sort of come across. Um, it'd be good if I had a small data set, right? So instead of fitting 1,000 models, if I'm fitting maybe 50, and if I have if I'm using an algorithm that's pretty efficient, not super computationally intensive. Um, Even with those, K-fold is really the way to go. So let's talk about K-fold cross-validation and what that means. Okay, so we're gonna split the data into sort of these things are called folds, but you know, split the not we're not splitting the data, but we're gonna do this thing. Um, no, we're gonna choose K folds, right? So we're gonna split the data into, let's say I'm doing 5 or 3-fold cross-validation, right? So I'm gonna split the data into 3 separate groups, right? And then each one is going to end up being a held out data set. So I'm going to train the data on 2 of my folds, and I'm going to validate on that third fold, right? And I'm going to repeat this thing however k times, right? So first I'm going to fit on folds 1 and 2 and validate on 3. Second time I'm going to fit on 2 and 3, and I'll validate on 1, right? Third time, I'm going to fit my model on 1 and 3, and I'm going to validate on 2, right? And then sort of we aggregate the performance, right? So we'll look at those out of sample performances of root mean squared error or AUC, and and then we'll sort of have a lot of those different measures of performance, and then we'll sort of talk about what is the average and what is the spread around it. So my example, and we'll do the example sort of visually in a second here, of 3 is not usually used. So usually you'll either do 5-fold or 10-fold cross-validation. And that choice of 5 or 10 is kind of dependent on how computationally intense the algorithm is, similar to the leave one out cross-validation. Like, if, if I'm doing 10, that means I'm fitting 10 models or fitting the model 10 times. And if it sort of takes a long time or is super computationally intensive, maybe I don't want to do that. Or it could also be a question of how much data do I have, right? So if I've got less data, maybe I would choose 5 because if I choose 10, then my holdout sample might be really kind of small. But like I said, this isn't something that this is a choice that is made and kind of you live with it. You don't kind of revisit this choice later on. Like you wouldn't say like I did 5-fold cross validation and compared it to the performance if I did 10-fold cross validation. That kind of you're not really comparing two different things. You're kind of comparing two sort of attempts at estimating the same thing. So it's not really meaningful in that way. So, you make that choice of 5 or 10 and you kind of go on with your life. So this is kind of the visual here, right? So, we would start with all of our data that we've collected. We would still do our split of training and testing, right? So we're going to hold out this data set. But then we'll do these K folds, right? So we'll resample uh, one, right? Where in resample one, we'll sort of fit our data on maybe the folds 2 through 10, right? And we'll assess the model performance. And this is kind of getting to a little bit of some of the terminology or nomenclature here. But we're on that first split, we talk about training and testing. But when we're doing our in this resample, so that we don't confuse ourselves, even though it can be confusing, we fit our models on an analysis data set, right? And then we evaluate the model performance on the assessment data set. So we don't really call these train tests. We call it analysis assessment because this is the train test split that happened already, right? So here's like a little visualization of threefold cross-validation. Let's say we had a data set of 30 observations. We would kind of group it into 3 groups of 10, right? So in this example, we've got a green group, right, of green circles, and each one of them has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For some reason, that's not a circle, that's like a square, but that's fine. And then we've got a blue group. So we've got 10 blues, right? These are randomly assigned. And then we've got like yellowish, tannish squares here, right? So, but what we've done is we've kind of taken our 30 observations and randomly assigned each observation into 1 of 3 groups. And then when we do these folds, right, we're going to fit a model on 2 of the folds. So in this case, it's only the blue and the yellow. And then we'll estimate the model performance on the remaining part, the green squares, green circles. And then similarly for fold 2, we'll fit on the blue and the green, and then we'll look at the performance on the yellow ones. And then for fold 3, we'll do yellow and green, and then we'll fit it on the blue held out sample. But what's kind of nice about this is that every observation ends up being in an evaluation data set exactly once, which is pretty good. So that's threefold. I'm using the example of 3 here because it's easy to put on a page. Like we said earlier, generally speaking, we'll be doing 5 or 10 for holdout for folds. So you'll do either 5-fold or 10-fold. And normally you have like way more than 30 data points. So like, why do we use this, right? So it tends to be a good compromise. It's more stable than the one split approach, right? Because we're doing this thing repeatedly. But it's also less computationally expensive than leave one out cross validation, right? So we're either doing 5 or 10 model fits. We're not doing, if we had 1,000 data points, 1,000 data model fits. Or if we had like 1,000,000 data points, we would have to do 1,000,000 fits of a model. So, it's kind of a nice in between, and it works well for many model classes. So, a little intuition behind the choice of K here, right? So if we choose a 5, right, I'm kind of saying we have 2 choices, either 5 or 10, right? So if we choose 5, we get a bigger validation fold, right? So we'll have more data in there and we'll fit fewer models, but we might get a noisier estimate of the model performance. So sometimes noisier, but it's oftentimes faster because we're fitting fewer models. So if I have like a really expensive model that like takes a long time to run and costs a lot, like I have to run it in the cloud and I'm paying money for my cloud expense, maybe I would think about 5. With larger K, we have smaller validation data sets, right? Well, we have to fit more models, but oftentimes it's a bit more stable, right? Because we're getting 10 estimates of that model performance rather than just 5. And also, if I've got a lot of data, 1/10 of my data is in every validation fold. So if I've got a lot of data, I'm still getting a good uh, uh, data set, right, to perform my model validation. Um, so what? Okay, so like I've done all this work, right? I've split my data into a bunch of these like subgroups, and then let's say I'm doing tenfold cross validation. I split my data into 10 subgroups. I fit 10 models, and I for each of those 10 models, I evaluated the performance on that holdout data set. So what do I get? I get a set of scores, right? So I'll have, if, let's say I'm doing a classification problem, and I care about this AUC metric, right? So I would get 10 distinct values for AUC, right? So what I'm going to compute from that, I'm going to compute the mean value, the mean cross-validated AUC, right? And then I would sort of look at the standard deviation and the standard error across the fold. So I would get not only an estimate of the the point estimate by doing that mean, but then I'd have an idea of what the spread is around that mean, which could be helpful, right? Maybe I care about that. If the fold wise scores like vary a lot, right? So it might just uncover that we have a very unstable problem, right? Or it might mean that like our model is overfitting. So that would be bad. Um, or it might mean that like the model performance is sensitive to which observations we train on. Maybe there's some observation in there that like just really like kicks up my model performance, maybe. Right. So like we do care about this spread, right? But if we see like that scores are kind of tight, close to the mean, it means that performance is stable, and we probably can trust the model comparisons more. Um, so this is the sort of a slide that sort of explicitly talking to uh, the idea of like the train test split, right? So versus the analysis assessment split, right? So the big picture is we do a train test split. We use this training set to fit parameters. We apply cross validation to the training set, right? So that's kind of important because this test set is truly like a holdout thing that we're saving to the end of our work, so that we kind of look at this thing once and once only. But then within our cross validation, we're doing more splits of the data, right? So inside each fold, we're creating an analysis set, right? So this is like what we're gonna, within the cross validation, train our model on or fit the model. And then we're gonna apply the model to the assessment set to evaluate model performance. So we fit and we score the model within each fold, right? So that kind of, I am going to jump back here real quick. Hold on. I'm going to jump real quick back to like this this view because this one kind of sums it up, right? We split our data into train and test, and then we repeatedly split our training data into a bunch of resample resamples where we create an analysis and assessment out of each. And the idea is that every observation in our training data is going to end up exactly once in one of these assessment data sets. Okay, boom. So I wanted to reiterate that this idea of leakage. So all of this is trying to protect us from overfitting our model, but also from you know overusing that test data set. Right. So here, this is that test data set really is intended to be a final exam. So we shouldn't be choosing features based on how our model works on that, or tune any hyperparameters based on that, or choose any sort of thresholds based on that. It really is like the idea of that test data set is truly a final exam. Okay, I think we've sort of hammered that home. So here's sort of, when we're this is more of like a conceptual thing about like, well, when we're comparing two models, it's important, it's best practice, right? So we're going to repeatedly break up our data into all these little chunks and create these uh, you know assessment and analysis data sets from our training data. If we're comparing two models, it is kind of important that we use the same folds, right? So if we're doing a 10-fold cross validation, we want to do the same 10 folds we want to apply to model A and model B, and compute the performance uh, on the same exact sort of random assignment of do analysis and assessment. This is going to sort of take one source of noise out of the system, right? So you kind of don't want to have a completely different uh, uh, sort of random sampling approach for when you do this if you're comparing two models, because then you're adding an additional source of noise, right? So you get a fairer comparison between the two models. So it's a better approach there. Okay, and what's nice here is like we talked about last time, stratification is an important idea if we're looking at something where we have sort of an imbalanced class in the thing we're trying to predict. So like, for instance, in credit analysis, typically, unless you're dealing with like very, very, very subprime groups of borrowers, you're expecting default or lack of payment or even late payment to be kind of like a rare-ish event, right? So if we have a class imbalance, stratification is a really good idea. So when we build these folds, we should be thinking about preserving class proportions in those folds, because that's an even now we're talking about an even smaller uh, uh, population, right? So like, this is, if you don't sort of take care of this, you could end up with some folds that have like out of whack sampling within them, either too many or too few of the thing you're trying to predict, like default, and then you'll get a noisier outcome, right? So, and in the worst case scenario, you'll have outcomes where defaulters never end up in any of the folds, right? So that would be bad. You would basically get no measure of the performance there, so that would be kind of bad. But this reduces the variance in those metrics. Well, we talked about this already, right? That the preferred method for classification is AUC, right? That's one that is invariant class imbalance, and actually it supports decisions that you might make to optimize business objectives, right? So like something like a threshold for a credit score. Do uh, lend, don't lend. It might be driven by sort of you could use the AUC as a tool to help you make that decision. So AUC is kind of the way to go. Okay, so that's like we're gonna lean into cross validation um, in our live coding. So you're gonna have an example of that. But I did want to just speak to, just so that for completeness, and so that if it comes up, you'll have some sort of a frame of reference for what these things mean. Um, so bootstrap resampling is a is a an alternative to what I described with the k-fold cross validation, um, but it's just a bit different, right? So the idea with a bootstrap is we sample. Let's say we have our 30 observations. We sample these observations with replacement so that we can get sort of multiple hits of certain observations, right? So in this case, the first one was included twice, 8 was included twice, 16 was included 3 times, right? So since we only have 30 observations in the whole thing, right? Some of our observations are not going to be included in the population, right? So anyone who wasn't included gets included in the holdout sample, right? So we create the bootstrap by sampling with replacement so that we can get multiple observations in there. We fit on this bootstrap sample, and then we evaluate performance on the out of bag observations. So whoever wasn't selected gets put into the uh, model, this performance data set. And we repeat this many times. So the couple things about this approach is that um, we don't have to pick a K here, so we could repeat this as many times as we want. So we could repeat this 1,000 times, right? And then we could sort of probably get a pretty good estimate of that performance, right? So you repeat this as many times as you want, and the more times you repeat it, you're getting a better and better fidelity on that distribution of performance. But the downside is you're really not guaranteed to have every observation included in any of these out of bag uh, validation sets, which maybe you care about. But this is Bootstrap. It's similar, but has slightly different. um, so with cross validation, comparing the two, cross validation kind of would ask answer the question: how good is the model out of sample? The bootstrap would kind of say how variable is my estimate of the performance, or like what is, like I said, you can create with high fidelity the distribution of model performance. So this would sort of give you sort of a good idea of the variability of that estimate. So they're not exactly the same, slightly different utility there, but that's kind of the mental model there. All right, and then so for time series, like I said, a bit of a different approach here, right? So our random splits. So we don't want to do random splits because our data very likely has some sort of temporal structure, right? We're very likely dealing with economic cycles potentially that are going to impact the data. So we don't want to just randomly pick a bunch of our data points. These things kind of should have some sort of like time dependence, right? And the other thing is if we just do this random thing, like it kind of leaks future outcomes into the past, which is bad. So the better idea, and I apologize, this is a very tiny image of what's going on here, but we sort of create these rolling windows, right? So let's say we had 15. I wonder if I can sort of zoom in here. No, can't. Uh, let me see if I could kind of make this thing bigger. There we go. Um, so here we have, let's say we had 15 observations, but they're ordered by time. The idea would be we would fit the model, uh, you know, using, in this case, 8 observations, right? Or 8 time buckets. Maybe each one of these corresponds to a year or a quarter, right? So we would fit the model on 8 years of data. And then we would evaluate the performance on, years 9, 10, 11. And then we would kind of move it forward 1 year, right? So then we would fit the model on years 2 through 9 and evaluate the performance on 10 through 12, right? So in this way, we're sort of preserving the temporal nature of the data. We're trying to use past data to predict future stuff, but we're also still able to get, um, you know, uh, a lot of different views on the model uh, performance, right? So in this case, we would have 5 different sort of calculations of how does our model perform. So this is the rolling window approach to resampling, and it is kind of important to use if you're doing anything time series related. Um, okay. I mean, obviously, like it is limited to, if these were years, I would need to have 15 years of data, which sometimes can be problematic, right? So uh, lots of times you'll find that like people start collecting data, and then like a couple years in, they're like, wow, we've got all this data. And can we build a robust model? And it's kind of like we're kind of dealing with 2 years of data, and we really haven't seen a cycle of any of this stuff recently. So data is, very valuable. So if you've got a lot of long history of data, this is a great approach. Okay, so I wanted to sort of discuss quickly the the um, the package that we're going to use to do our cross validation. So we use this package called rsample to do our to do our train test split. Remember, there was a function called initial split. Rsample can also do cross validation, right? So uh, we talked all about that, right? So here, right, if we're doing our single split, and we should remember we should still do this, right? So we can take our data, we can put it into this initial split function, and this proportion kind of tells me I'm going to get 70% in my training and the remaining 30% is going to be in my testing. And then we call these functions training and testing in the object that comes out of this thing. And this will give me the random 70% and then the corresponding 30% that was left out. It's a similar thing here, right? But we're going to do a vfold. The function is called vfold CV. I apologize for using the term kfold earlier, but it's vfold for the function. And here we would say we're going to create 10 of them. And then we use, this will come out with a thing that's a list type of an object. And we'll see it in the code that we use. So we can call analysis and assessment to pull out the corresponding data sets. I do think in this code example, I would need to kind of like say which fold I care about. So it would be like split, 1 through 10. So you'll see it in the code that we're going to use tonight. So This returns a tibble, right, with an ID for each fold and splits column, right? So each row contains one split object. So we're going to get a thing that has 10 rows in it, but some of our columns are going to have multiple, sort of, they're going to be more list type objects in there, right? So it's going to be like each cell will correspond to one of these split objects, and we can look at it. We'll see it in the example. So um, we already talked about this. We're going to fit our data on the analysis set and evaluate performance on the assessment set. And like I said, we have this strata parameter here, right? So if we have some sort of imbalanced data set where the thing we're trying to predict is rare, we can use this strata parameter. That's going to make sure that like the class proportions are similar in each fold, right? So we can avoid that situation where some folds maybe have almost no or no events in a given fold, right? So just to hammer it home one more time, and I apologize. These are kind of new slides, right? So it's a little bit repetitive. We do our train test split, and then we create the folds within our training data. So, so if you remember, I guess 3 things, right? One, split is noisy. Cross-validation gives us a distribution of outcomes and not a single number, right? So we'll have a good idea of like a true, and because like all of the performance metrics that we're calculating are on out of sample data, right? This a cross-validation performance metric like AUC can be interpreted as how will this model perform when we get to new data, because we're always evaluating model performance on data that the model has not seen, right? Not only do we get that estimate, but we get a lot of those estimates, so we can create a distribution of these performances. And then the other thing is like that test set is really for the final exam. So we are going to take a 7:30 right now. We are going to take a quick break. We'll take a 15-minute break. I'm going to get some water, maybe make some tea. We'll be back at 7:45, and we'll pick it up. We're going to introduce a new modeling approach called K-Nearest Neighbors. And then we'll talk about, we'll do some live coding session. So I'm going to turn off my sharing here. And we'll be back in 15 minutes. Okay, see you in 15. Thanks, everybody. All right, we're back. Okay, so can everyone hear me? Just checking if you can hear me, please raise your hand. Okay, wonderful. Thank you. Great. Okay, so let me boom, go back here, share my screen. Okay. Sorry about this. I'm having some technical difficulties. Okay, there we go. That was harder than it should have been. All right. All right, so we're going to talk a little bit more in detail about the application and why you use resampling, um, and uh, and also we'll introduce a new model algorithm that we haven't talked about, K-nearest neighbors, yet. So we'll kind of introduce that, and then we'll do a little bit of a live coding thing so that um, you'll be able to see this stuff a little bit in action. So K-nearest neighbors. Um, so how does this thing work, right? So we are going to make our prediction for a given observation by looking at the K, the some number of observations within the training set that are close to our new observation, right? So that we'll look at the K closest training observation. And so for each classification, for classification, right? So if we're doing a classification problem, each neighbor essentially votes, uh, and the prediction, this would be more of like a hard prediction, right? So we can choose the most frequently occurring class amongst the neighbors, or if we have a high enough K, we could look at the proportion, the percentage that had the particular class that we were looking at. So prediction could be a class label. Okay, so it could either be a class label of the most frequently occurring or a probability estimate from the vote share. So let's say we were doing 10 nearest neighbors, and 9 were not defaulted and 1 was a default. We would probably say, oh, well, we'll assume this guy's not a defaulter, but we would give it a 10% probability of being a defaulter. So you could see like this probability, it's an estimate. It might be a little bit noisy, especially if we choose like a low number for that K. So you can think of this as like there's a geometric sort of model that we could use. Think of each observation as a point in feature space, right? So if we had 2 features, then it's kind of easy to imagine, right? Like we would imagine a 2-dimensional plane. And actually, I don't use this example anymore, but I used to use an example that was house price data in a town in Iowa called Ames, Iowa. And actually, I think it was Ames, Iowa, because they have a really good statistics department at not University of Iowa, Iowa State is in Ames, Iowa. So in this data, they were using latitude and longitude as your sort of the two features. So in that case, it's like very directly near neighbors, right? These are houses that are geographically close to the house that you're looking at. But you know, if we have 20 features, it's a similar idea, but you can't really like imagine 20 dimensional space. That kind of gets a little bit. I certainly can't. I have a hard time with three-dimensional space. So 20 features gets very hard to visualize. But KNN would say, look at this new point. What do its neighbors do? What do other observations that are close to this one do? Right. So in this algorithm, distance is the whole game, right? So it depends on a distance metric, usually Euclidean distance. So that would mean like, um, you know, a direct line, right? If I had 2 points in two-dimensional space, Euclidean distance is just drawing a direct line between the 2 points and measuring the length of that line, right? But there are other sort of distance measures you could use. One of them is called Manhattan distance. We're not going to use it. There's a couple of other ones, but usually we just pick Euclidean distance. And scaling matters. Scaling of the features matter, right? So we'll talk a little bit about feature engineering and data pre-processing, but like we had two features like height in pounds and weight in height in feet and weight in pounds. Those two things have two different scales. So like I think you unless you did something there, then you would find that the weight is going to dominate just because like pounds usually have a lot more you know, I have more me in particular, I have more pounds of weight than feet in height, you know. And it's also going to matter on which features are included. So like KNN is as much about the features as it is about the algorithm. And a big a big choice here that we would need to make is this idea of K. You could think of it as a dial, right? Um, so the K is how many neighbors am I going to consider in this algorithm, right? So if I pick a small K, right, this would mean I have a very flexible boundary, right? So I would see a lot more variability in this the outcome here, depending on sort of which data I fed into this thing. Um, it can memorize training data. So this is sort of like a hint that like you may be in a situation where overfitting would be an issue, right? So we would really want to be very worried about overfitting, and we would really want to get a estimate of the performance that depends on out of sample data, right? So this is like a big deal, and the measure of performance would probably have high variance, meaning that if I picked different training data, I would get a wildly different model. But if I pick a large value of k, it really smooths stuff out, right? So I'm taking an average across a lot more of my population, right? So I would probably get a lot less variance, smooth noise, but this would have a higher bias and maybe less able um, to sort of uh, do a reasonably good job at estimating the thing, right? But I would have a lot more stability. So the example here would be like, you know, houses in, you know, if I was looking at house price, right, and I picked, you know, 5 neighbors, right? And if I picked a house in like a mansion in Greenwich, Connecticut, it's very likely that like the 5 neighbors are going to be other mansions. So I probably get a more meaningful result. Whereas if I picked like 1,000 houses, I'm probably picking up houses in Stamford and in Port Chester, which probably are not mansions. So I would get a much smoother estimate there. So K does matter a lot. And like I said, K is not going to be like a parameter. I mean, K nearest neighbors is a non-parametric thing. Like there are no parameters estimated. It's all driven by the data, right? So this is not, the data isn't going to tell you what value to pick from K, so of K. So, but there may be an optimal choice there to be made. So K is what's known as a hyperparameter. It's a model setting we choose before fitting that controls model complexity, right? So KNN's hyperparameter is K, but there are other modeling algorithms that also have hyperparameters. So next week we'll talk about another algorithm called Ridge Lasso. This is called regularized regression, and this has a parameter called lambda. Or if I'm doing a regression on a nonlinear regression, I'm choosing a polynomial, and the degree of the polynomial is a hyperparameter. And when Professor Hayes picks up the class and starts talking to you about tree-based models, right? So these have parameters such as max depth, amongst others. So hyperparameters are, once again, these are things that like you need to choose. They don't come directly from the data, but you'll see that with resampling, because we're sort of repeatedly analyzing model performance out of sample, that we can use resampling to help us pick these things, right? So we can look at a lot of different values of K, and depending on the out of sample performance we see in our v-fold cross validation, we will maybe get an insight into what a good value of K might be. So parameters are different than hyperparameters, right? So parameters are what we learn from the training data, like the coefficients in our regression, whereas hyperparameters, we have to choose them, but we will use a tool to help us choose them. So when we do our live coding session, we will choose a good value of K using cross-validation. You'll see that in action. And we're going to introduce, so we've already seen the default data that comes with our ISLR book in the ISLR2 package, but we're going to be looking at a different data set. So a quick introduction to this Caravan data set. So while it's not like finance data set, it still has some business sort of application. It's an insurance marketing data set, and we're going to be looking at this column called purchase. So this is like each row corresponds to a different customer, and there's a lot of different predictors, many customer features such as demographics and prior products. There's on the order of 80 or so predictors, and there's a single outcome, which is a binary outcome. Did the customer purchase the insurance? So the outcome is rare, and the signal is weak and spread across many features. So we will use that one for our example here. So we talked earlier about like how small k is a high variance, low bias type of a model, right? So you're going to get potentially a good, if we choose a small k, potentially a good prediction of what we're looking at, and particularly you'll get probably a very good in sample a prediction that performs very well in sample. But we'll see that like it might look great in sample, but we might see some degradation out of sample when we try to see how this thing looks on new data. So cross-validation gives us a principled way to choose the value of that hyperparameter K. Um, and we will be using AUC. So just sort of a reminder about why we use AUC. Um, when we talk about accurate, remember we talked about accuracy. If we have rare events, we can get a very high accuracy by just predicting no for everyone. But we will be looking at AUC, which is, like I said earlier, insensitive to class imbalance in our data. So remember, we're talking about distances, right? So, and I said, like, if latitude and longitude are great because essentially they're sort of on the same scale. 1 degree of latitude is about the same as 1 degree of longitude, unless I'm near like the North Pole or something like that. But since we're using distances, we need to uh, be aware of the scale of of our of our features, right? So if one variable has a bigger numeric range, right? So let's say one variable is like dollars that goes between you know uh, 0 and $10 million, right? And another variable is something like uh, height in inches, right? So that would be somewhere between like probably, I don't know, uh, 50 and 80 or something like that. 80 would be extremely tall, but you know what I mean. The one that has a bigger numeric range is going to dominate our distance metric, right? So our neighbors are chosen based on units, not information. So one thing we're going to have to do is center and scale our data, right? So we're going to have to make sure that these things are all that's called normalization. We need to make sure that once we center and scale, right? So we're going to subtract the mean and divide by the standard deviation. That's what center and scale means. These things will all be normalized. So if we were to look at any variable or at the distribution of the variables within our data, we would see that each one of those has a mean of 0 and a standard deviation of 1 after centering and scaling. So this is an algorithm where like we have to do some sort of pre-processing or else the algorithm will break, right? If all of my features in my data are all in different units and with different scales, then KNN is not really going to do a good job because we're doing distance. Like I said, normally we're doing Euclidean distance there. So center and scale, what is the algorithm for that, right? So we take our value and we subtract the mean, and this is kind of important, right? So we're going to take the mean of the data we see in the training data set. This is a sort of uh, a thing that will protect us from any sort of leakage. We want to be sure that we're kind of always, any data type of operation we're doing, and this is one, we're calculating some statistic of our data. We really only want to look at that mean of the training data set. And similarly, when we scale, we're going to take that centered value, we're going to divide it by the standard deviation, the sample standard deviation of our training data set. So we do this using training statistics only, right? We don't look at we certainly don't look at the test data set. And we even maintain this sort of relationship when we're doing things within our cross validation. So we would center it based on the the analysis data set. So the correct approach is to compute the mean and standard deviation on the training fold and apply that to the validation fold. Right? The incorrect approach would be to compute the mean and standard deviation on the full data set. The idea is you really want to, if you're ever going to build a model on one thing and do the performance model, the model performance, calculate the model performance metric on that out of sample thing. You want it to truly be out of sample. You want it to be as if I had never seen this data. If you evaluate on the training data, So this is sort of the idea of like in sample performance versus out of sample because k nearest neighbors in particular, especially for small values of k, is a high variance, low bias model, right? The It's highly susceptible to overfitting, right? So if we evaluate our model on the training data, we can get really great, looks like we have really great performance on small values of k, but we're actually measuring memorization. This model memorizes the data, right? So there's no guarantee that like whatever results we get are going to generalize to new data, right? So if we evaluate on the held out data, we'll see that the small k often degrades. It looks great in sample, but that looks less great out of sample. And usually there's a sweet spot where it looks good in sample and good out of sample, right? Because we'll kind of find some level of k where it's we're getting some good performance, right? It's flexible enough to do a good job of modeling our data, but it's not so overly smoothed out that we actually get some information there, right? So we'll see how that works in practice. We'll evaluate sort of the model performance across different values of k and see if we can identify a sweet spot. Um, this is kind of the extreme, the intuition around like this why small k can overfit. Uh, like if I picked k equals 1, this is like the extreme version, right? If my data is in sample, right, I would actually pick the property that I that I uh, if I'm, let's say I'm doing house prices, I pick the one nearest neighbor since that house is in my data sample, right? It would be its own best neighbor, right? So noise points can dominate predictions locally. Um, KNN is does have some downsides to it. Um, it often struggles when features are highly dimensional, right? So this is something called the curse of dimensionality, right? So if you have too many dimensions, you may find that like certain points have very few close neighbors, right? So neighbors might be actually quite far away within high dimensions, right? So this is kind of like a well-known thing, and it actually has its own name, the curse of dimensionality. Um, uh, KNN could struggle when the signal is like a linear signal, like right. So like uh, you might find that a simple linear regression or logistic regression may win. If you have a lot of features that are irrelevant, right? KNN doesn't do feature selection. So if you've got a lot of irrelevant features, it could really muddy the waters, right? Because you're going to be determining who's my closest neighbor based on these features that don't actually matter. Or if it also doesn't do a particularly good job if I've got missing data or missing data elements within my data, right? So distance can become messy if I've got missing data, right? So just a little extra note on the curse of dimensionality. As the number of features grow, um, near neighbors become a little less distinct, right? So you may find that I actually don't have any close neighbors because I've got so many dimensions, or distances can bunch together. Um, so with a lot of dimensions, you may need more data to get stable neighborhoods. Uh, so feature engineering and sometimes feature selection helps. So we'll talk a little bit about feature engineering in a bit here. So this is kind of the algorithm we're going to use to, it's called hyperparameter tuning, and we're going to use cross validation, V-fold cross validation to help us out. So the algorithm is we'll split the data into our train tests. We kind of always do this. We'll set aside the test data as a final exam. We're going to create these folds inside the training data. And then for each value of K in a grid, and the term grid really only means some pre-selected values of the hyperparameter that we want to consider. So we're going to create a grid of Ks, right? So you might think in your brain like, oh, grid would be like a two-dimensional thing. In this case, it's a one-dimensional grid, right? We're going to pick some number of values of K that we feel does a good job of sort of uh, being values that we may want to consider, right? So, but for each one of these values, we're gonna do our scaling within the analysis data set within that grid, right? So that we don't have to deal with sort of different features on different scales. We're gonna fit, so we're gonna center and scale. We're gonna create a model, we're gonna fit a model, and then we're gonna predict it on the analysis data set. We're gonna compute uh, our performance metric on the validation fold, right? And then we're gonna sort of look at the performance, both the distribution, but also the average performance uh, across all of those folds, and we're gonna see which value of K ends up with the best average cross-validated AUC. And then once we're done, we're going to evaluate on the test data set. So we're going to, once we're done, right, we'll have picked a K. We're going to fit a model on the entire training data set. And then we're going to evaluate the performance on the test data set. And we're going to do that tonight in the live coding session. So grid search is easy and transparent. There's actually like a lot of different sort of much more calculated, sort of esoteric and sort of deep domain like search type algorithms, but we're keeping it simple. We're not doing any sort of like gradient descent or very fancy things. We're the grid approach is like perfectly fine. And you can try to find a sensible range of values, right? So typically you would pick some values sort of that looked a little bit like this, right? 1, 3, 5, 11, whatever. And and then you could refine it. Like, let's say you saw like good performance around 25, right? So you saw like, let's say your out of sample performance was really bad, really, really bad, got better, got pretty good around 25, and then started degrading out here. You could sort of do a second grid that's sort of more localized around that 25 to actually pick a better value. So this is like a wide grid with some pretty big gaps, but it should give you a good idea about like where that sweet spot may lie. You don't have to do every value of K is kind of the message here. And a typical pattern would be that like the training AUC decreases as K increases, right? Because we are taking like more population averages and applying them to every sort of observation in our training data set. So we would expect the training performance to decrease as K increases. But our validation AUC, this is our like cross-validated, we can think about this as like our out of sample performance would improve and then maybe plateau, and then it actually can get worse, right? So this would help us find a good choice for this K value. Once again, we're not I mean, I know I'm being quite repetitive here, so I apologize for that. But when we look at our cross-validation performance metric, we're going to have not just an average performance metric, but also a standard deviation across the different folds. And this will give us an idea of the point estimate, but also how stable that estimate is. Okay, so we kind of alluded to like we have to do some sort of pre-processing on our data, like it's required for k-nearest neighbors because we're doing a distance metric, right? Because we care about how far the points are away from each other, how similar or dissimilar the points are. But like this is kind of dipping our toe into a whole, actually, one of the books in the syllabus is all about feature engineering. It's just called feature engineering. So like this is a pretty deep domain type of a thing. So I just wanted to give a little bit of a quick overview of like what is feature engineering and what its utility is. Like I said, for k-nearest neighbors, we have to do it because we care about distance and we got to make sure we center and scale everything so that the scale of the feature doesn't end up being a big problem for us. So what is feature engineering? It's changing the representation of inputs to make learning easier, right? To it, so our goals are we can capture the relationship more directly, but also we can make the algorithm behave well, right? So we can stabilize the algorithm. Um, so sometimes the algorithm we choose requires us to do some level of feature engineering. So for k-nearest neighbors, for example, like scaling is really important. We would, because we know that irrelevant features could be problematic, we would want to maybe remove some features that we deem to be irrelevant. And missingness is a problem here. So um, some of the uh, some of the remediation approaches, there are sort of feature engineering remediation approaches, such as like you could put in sort of either an average, a population average for missing data, or possibly like if it's a categorical variable, you could like put the most frequently occurring, or you could build a model to try to help you predict this missing data. You can get pretty fancy with the feature engineering. For linear and logistic regression, outliers are a big problem. So we might want to sort of like rescale our data or do some transformation on it to sort of mitigate outliers. So like you'll see that for financial data, lots of times if I've got highly skewed data, I would take the logarithm of something, and that would sort of reduce the skew of my data. Nonlinearity or multicollinearity are problematic for linear regression. So there are some remediations there. Missingness is also a problem for linear regression. So if you can't run a regression with missing data, so you would have to do something about those. And you could drop any rows that have missing data, but you would want to be judicious about that. That's kind of a choice you'd make. Tree models, which Professor Hayes is going to get a lot more involved with. Scaling isn't as much of an issue. Nonlinearity isn't much of an issue, but like you do have to be concerned about overfitting. And many methods, class imbalance can be a real issue. So you might want to do some sort of feature engineering to help manage those things. So like here, some common operations that you might see. We're going to get really into scaling and standardizing, centering and scaling our data tonight. We're going to do that. We've already seen like the encoding of categorical variables by using dummy variables. That kind of comes for free when we're feeding any sort of categorical or factor variable into the regression algorithms in R, like LM or GLM, linear model or generalized linear model. It kind of automatically creates dummy variables for us. But that actually is, even though it happens kind of automatically and without us thinking about it much, that is a type of feature engineering. It's taking one variable and creating, in this case, one or more additional variables that are going to have either a binomial or Bernoulli sort of encoding there, 1, 0 are going to be in there. We can transform our data. So like I said, you'll see it a lot. People take the log of a price. That's going to, or the log of a return. That's going to sort of address any sort of skew we might see, or you can take the square root. Winsorization is a term that just means any values above a certain threshold. I'm just going to sort of assign that threshold. So if I was winsorizing my data, that would mean that like I would calculate what the 95th percentile is. So let's say the 95th percentile is $100 or 100 whatevers. Anytime I saw a value above that number, I would just assign 100, and that just sort of chops off the outliers, and you sort of would have a potentially better behaving data. You could take ratios of variables. So this happens a lot in, like, if you're doing a model where you're sort of looking at financial values off of balance sheet or cash flow statements. You might take ratios. You can look at interactions. This is where you kind of multiply two values together and understand how they move together. There's a lot here, right? You can bin your data. You can sort of do splines of your data to sort of get sort of an expression of nonlinear relationships. You can impute missing data, right? And then finally, like if you had an algorithm that was very sensitive to class imbalance, you could oversample sort of the underrepresented class, or you could undersample the majority class, right? So this would be like you're actually taking, your very few defaulters, and you're sort of you're putting them back in the population multiple times to get a better split between, default, non-default. Or you're actually going to maybe potentially throw away some of your data. So you'd throw out a bunch of the non-defaulters just so that you get a better sort of split there. So we're not going to get like too involved, but like I just wanted to sort of throw this out there that there are a lot of approaches that can be taken to sort of like do stuff to your data to make it more amenable to whatever modeling exercise you're trying to undertake. We're going to talk about centering and scaling tonight, but if you want to like look more into these things, like I said, the book on the syllabus, Feature Engineering, kind of really goes into depth about these things. So like tonight we're going to be looking at scaling and normalization. So like it's used for when we have things that care about distance. But then we'll also see it next week when we look at these regularized regression. So these things do depend on the scale is very important. So you need to understand everything needs to be on the same scale. So it's like requirement of the ridge or the lasso to do centering and scaling. Or if we're doing some sort of gradient-based model, right? So these things, everything needs to be on the same scale, mean 0, standard deviation 1. Things, you don't really need to center and scale your data if you're doing decision trees or random forests. These things are not particularly negatively impacted by any sort of scale issues in your features. So, but okay. So transformations in the finance examples, right? We talked about that log, especially with these things that could be highly skewed, like income or balances or house prices or that thing. You can do a transformation, a log transformation to reduce the skew, address the outliers, or you could sort of directly just tame these outliers. You could chop them off. But anytime you need to stabilize the variance of your of the feature in your data, you could probably evaluate different transformations to see which one kind of did the best job. Lots of times you know, especially with like regression problems, if you look at the distribution of a particular feature, it's usually ideal if that thing has something that kind of looks like a normal distribution, like it's got a hump with you know, with some sort of spread around it, right? Um, we talked about encoding categorical variables. Like I said, we've actually done this with some of our regressions when we put a factor variable in there. Kind of happens for free, right? So one thing that you might hear is it can be called a one hot encoding. It just means we created dummy variables. Um, um, Interactions, right? So, maybe it's not the case that every sort of variable kind of operates on its own. Maybe we have an idea that like two variables might sort of work in tandem. So we can include an interaction term, or we can create a ratio, right? So the interpretation of this would be like the slope or the marginal effect that I'm capturing here might depend on some other feature. Right? Um, when we did linear regression, we could capture nonlinear effects if we added, nonlinear transformations of some of our features. So we could create splines, we could create polynomial terms. In fact, there's a class of models that I'm not sure if Professor Hayes will get too involved in this, generalized additive models, but actually we've used these on my job quite frequently. They do a good job of capturing like non-linearity. So, one of the assumptions of linear regression is that like a linear relationship exists, and rarely does that really happen in the real world. Non-linearities are kind of all over the place. So we're probably not going to talk too much about generalized additive models, but they are quite interesting because they sort of directly model nonlinear effects, right? So we will see some of this stuff next week when we get into regularized regression. Um, we talked a little bit about missing data, which can be problematic, right? So if you wanted to, if you had a model that was not friendly with missing data, you would need to figure out a way to either throw out the missing data or not use that algorithm or come up with some way to sort of fill in the missing data, right? So you could do an imputation. You can have an indicator for that and then do an interaction. Um, or you could just sort of pick a different approach that handle if you have a lot of missing data, right? Then you probably would have to like sideline a particular modeling approach. But the key point here is like sometimes you adapt the data, not the algorithm, right? So if you really wanted to use k nearest neighbors, you could remediate missing data by like imputing missing values, right? By taking like a mean or a median or a mode of some variable, some feature in your data. Um, and we did talk about class imbalance, right? Like you could do some feature engineering to address class imbalance. We talked about this a little bit a couple of minutes ago. You could oversample the minority class, take repeated observations of your defaulters and put them into your development data so that you oversample that minority class. or you undersample the majority class, so you throw out some observations. I always feel a little bit queasy about throwing out data, but okay. So this is kind of like similar to the idea we were talking about. This can get kind of hairy and gnarly. So, but this is more of like a rule, best practice type of a thing. So if the transformation uses some sort of statistics from my data, like scaling or imputation, or we didn't even talk about this. This stands for principal component analysis, right? Technically, you really should be sort of like calculating those statistics on your training fold and then applying them to the validation fold. So leakage is a concern there, but also like you may get an optimistic sort of view of how your test metrics performs. So this can become kind of cumbersome in practice. We're not really getting too uh, overly concerned about this. There are tools out there in the R programming language that kind of make this a little bit easier, and I used to teach them pretty as part of this class, but they kind of it's like a whole thing, right? Like it's we don't really. I'm just trying to teach you like the fundamental concepts here. I'm not trying to teach you the package called tidy models. This is not a class on tidy models. It's more of like a fundamentals of model building. But really, if you're sort of doing any sort of looking at any sort of statistics of my data, then technically you really should be sort of like calculating those statistics only on the data that you're using to train, and that happens like within these cross validation folds, and then applying them to the validation fold rather than calculating the statistics on like the whole data. That's not You're not supposed to do that. And actually, in the example, you'll kind of see how that works. Okay, so we're going to do the example now. All right, so let's get ready for some live coding here. Okay, so let's do a little bit of a switcheroo. And this code is available in Husky CT. I also put it up onto the Git repository. So we're going to be looking at our Lecture 6 demo. Okay, so I would encourage you to download this script. It's kind of standalone, so you could run it from top to bottom, and you could run it and look at it for reference. Okay, so as we always start, we're going to load the libraries we want to use tonight. So we'll be using dplyr. All right, so this is we talked a lot about dplyr. That's sort of for manipulating data. R sample is what we're going to use to help us do our train test split, but also set up our cross validation folds. We've looked at yardstick, right? So yardstick is one that sort of helps us calculate model performance very simply, or simply, I'd say. This is a new one you haven't seen. This one is a library that implements k-nearest neighbors. So we're going to use kknn. And then tidyr is another sort of data manipulation one. And this package, ISLR2, is the one that has the data we're going to use for doing our model fitting. It's got the default data in there, but then it also has that caravan data. So since the resampling sort of stuff we are going to do involves some sort of random number generation, anytime you're going to do any sort of random number generation, you're going to want to do this set seed command. So the number in here really doesn't matter. You can pick any number you'd like, but this is going to allow us to replicate our results if we ever needed to. So it's more of a computer science type of a thing than than a model building thing, but this is really good practice here. So we're just gonna put that default data set into a local variable called df. So this default here comes in the ISLR2 package. So I could do questions default, and it would sort of tell me this comes from ISLR2, but then it would also give me sort of some information about what it is and where it comes from and all that stuff. So it's kind of helpful. Okay, so I've got 10,000 observations of 4 variables. So here we're going to do 5. So we're looking at a single split, right? So we're going to compare. We're going to see what happens if we do 5 different times, just a single split, right? Not doing cross validation yet, right? So here, and we're going to do tonight we're going to do a little bit more like programming type stuff in R. So I don't think we've seen this before, but this is like a for loop. This is how you do a for loop in R, right? So we're going to create an empty vector here that's going to store our results. We're going to call this thing AUC vec. And these are 5 numbers. And since we just kind of like created it empty, they'll have zeros in there. And here, say for some variable s, right? So s is going to, for each s, which is like the name of the thing we're going to do, and in this 1 through 5. So we're going to say like for s has values of 1 through 5, right? We're going to do everything that's contained in these curly brackets. So we're going to like repeat this code in here multiple times. So that's a for loop in R. So that's like the syntax. So if you've done any sort of programming, you should kind of be familiar with like what a for loop is. It allows us to repeat something over and over. So first time through, s is going to have a value of 1. And we're just going to set that seed of 1. So that's going to give us like a different randomness, right? And then what it'll do is we'll do these steps. We're going to do our initial split. Remember, this thing splits our data into a training data set and a testing data set. So we can create a train test. And then we'll just fit a model. Default is a function of balance, right? This is the logistic regression formula that we kind of saw. I don't know if it was last week or 2 weeks ago, but this is how you fit logistic regression. And this one here, family equals binomial, is the function parameter that you need to do logistic regression. But we actually did this line of code a few weeks ago. And then what we could do is we could use this fit model to help us predict probabilities of default, right? So this predict function takes a model, and we're going to create a new variable in there called p hat. And we can use this function from our yardstick package to calculate that area under the curve, right? So, and this pulled out estimate just grabs that out into like a number. So I could say here, I could run this code let me just assign a value of 1 here. And if I run everything in the loop, this will be sort of that first time through the loop. So I'm just going to set the seed because I assigned a value of 1 to s. It's going to say seed of 1. I'm going to do a train test split here using our sample, right? And now I've got a training data set that has 7,000, right? Because I said that my proportion is 7 to 70, 30. A testing data set with 3,000, and these are randomly assigned. and that randomness is getting driven by the seed I set here. I'm going to fit a logistic regression model. I'm going to add a column to my scored data set, to my test data set that has my probability of default. I'm using this predict function on that model I just fit. And I have a new data frame called scored, right? So here, if I do scored, you can see that this, if I compared this to the test data set, well, let me just do head of scored, right? So it's that the same test data set with all of my default student balance income. We're just looking at balance right now, but this p hat is the new column that I added, and I added it by predicting onto my model, right? So this is saying this is like a 0.12% chance of default, or this is a 1.84% chance of default, right? So not chance, probability. And then I can compute my AUC here, right? And you can see here that I'm reusing that S variable. So into the first element of AUC vec, I'm going to put my AUC score here. So now if I look at my AUC vec, that first one has a number associated with it, 941. But I don't need to sort of manually change this S. This for loop is going to change the S for me, and it's going to go 1 through 5. So if I just put my cursor here and hit Control Enter, it's going to run through all of that. And you see it went real fast, right? So because it's a computer, it does loops sometimes it does it quickly depending on what I'm trying to do. And I can create a little data frame from that. And I can see here that I'm getting, it's noisy, right? So this is sort of demonstrating that depending on randomly assigning values between my train and test data set, I can get different measures of this model performance from this. And a logistic regression is a low variance, high bias model, right? So, but I still see variance there. Sometimes it's 941, sometimes it's 950, right? And if I did more of that loop, then I would see sort of even bigger variance. So that's sort of getting to the point of like a single split is noisy, right? And it's kind of, remember we did that little poll earlier in class, right? That was, are any of these numbers wrong? No, they're all different estimates of some true performance that's out there in the world, right? It's just a noisy estimate. So let's compare that approach, right? Where we're just doing repeatedly doing a single split. Let's do a 10-fold cross-validation on the training set. Okay, so same idea here. We're going to set a new seed, and we're going to put our data into training and testing, which we kind of always do. Except this time we're going to create this, we're going to use this v-fold cross-validation, right? So we only do this on the training data. We're sort of putting this test data aside to the very end. We don't really mess around with that. But we're going to create our 10-fold cross-validation. So let's just look at what that thing looks like. Folds 0. So here, I mean, if we look at, remember we did this train test split, right? So SP0 is an object that has training, testing, and total, right? So we kind of see this similar type of an object, right? Within this column of our data, within our splits column, right? So we've kind of taken the 7,000 observations in our training data, and we split it into different groups. 6,300, this is going to be, this is our analysis data set, and 700, I'm sorry, 6,300 is our, yeah, analysis data set, and the 700 is our assessment data set. And the thing is like across the 10 folds, every observation is contained in exactly one of the analysis data sets, right? Because we remember the cross validation splits the 7,000 into 10 distinct groups, and then each one is going to be the holdout, with the remaining 9 sort of contained in the analysis data set. This is kind of a weird type of an object, right? So we're going to do like the same thing. This is the fold AUC, right? And we're going to do a similar loop, right? So we're going to use our for loop once again. And this time we're going to go I in 1 to however many rows are in our little data frame here. And we know there's 10 because we did a 10-fold cross validation. So we're going to do for I in 1 through 10. And this thing is going to pull out this line of code is going to pull out this. So let's just make I equal to 1, and we'll sort of like step through this, like the thing within the loop here, right? So this is going to pull out that split thing, right? So split I is this type of object that has my data in it, split into different things, but I can feed split I to a function called analysis to get training and validation. I should have called this analysis and assessment, but you kind of get the idea. So my training data, if I look at that, has 6,300 rows in there, and it's the 9/10 of the training data is kind of in there. But this validation set, let's just do this down here, is the other the other 700 rows. Yeah. So I'm going to then fit a model on my analysis data, right? So I'm going to pass in here TR, right? And I'm going to create a scored data frame that has my predicted probability of default from that model we used on that we fit on that analysis data. So I can look at scored here. It's got 700 rows, and it has a new column called p hat, right? And then I'm going to use this function from Yardstick to calculate my AUC and put it into that first element of fold AUC, right? So if I sort of put my cursor at the top of this loop for I in 1 to n row folds, I can execute this and it's going to run the whole loop. And I can see I've got values in this output vector that I created. And here I can get an estimate, right? So this is sort of like, whereas, yeah, this is a realistic estimate of my the distribution of my model performance across the 10 folds, right? So here I can calculate a mean and a standard deviation. So we're getting a mean of 951, but we do have a 2% standard deviation. So we can actually visualize this. CV summary. And maybe I want to do a ggplot. And Okay, I gotta load my library ggplot2. Okay, I'm not doing this right, so I gotta remember I need to wrap that thing in an AES here that I can get. Interesting. It's got a little bit of noise to it, so it's not like a hump thing, but I wouldn't read too much into it. But it's centered around 951 plus or minus 0.02. Okay, so like that would be the exercise, right? So we've done a cross validation. We've sort of evaluated model performance. This model performance evaluation is kind of valuable, right? Because we believe that it gives me an assessment of how this model is going to perform out of sample. And maybe I've decided like this is good enough. I like an AUC of 951. Let's go with it. So this is kind of like the end of the thing, right? So we're going to evaluate, so we're going to see how this model performs on our test data set. So we do a final fit. So that cross-validation stuff is really only used to help us sort of evaluate model performance at a sample, right? When we go to say like, this is the model we want to pick, we want to do a logistic regression, right? And this is the formula. We feed in the entire training data set and we refit the model, right? And now we can predict on that holdout set that we did up front, that test data set, right? So we fit the model on the full 7,000 variables that we have, observations we have in training. And we're going to look at the 3,000 that were held out at the beginning. And we're going to add that p-hat, the probability of default. Then we're going to measure our model performance on that test data set. And we see an AUC of 942. So we shouldn't be surprised that this is lower than the 951 that we sort of thought we were going to get, because it's definitely within sort of this distribution, right? So this is our model performance truly at a sample. This is the model performance on that holdout test data set. No leakage of information. We didn't do anything. We never touched this data to help us sort of evaluate model performance. But we do see that it sort of is in line with what we expected when we did our cross-validation model performance. All right, so that's for like using cross-validation to help us sort of understand how is our model going to perform at a sample. And that's like a big question. So the other sort of application of cross-validation, why we use it, is to help us sort of tune these hyperparameters that we need to sort of choose, right? So if we have k nearest neighbors, we have a hyperparameter k that we want to sort of evaluate. We want to find the optimal performance of k, right? So we're going to look at that different data set, that caravan data set. And this is a much bigger data set, right? Head, car, right? So it's got a lot of columns. It's got 86 columns. So there's 86 features in our data set. And we still have a fairly large number of observations, 5,822, right? But we're going to use nearest neighbors to help us do this, right? So we're going to use the X columns we care about are going to be everything except purchase, right? So this function setDiff kind of removes purchase. I mean, I guess we could have done like, we know that purchase is the 86th one, so we could have done like, rather than using setDiff, we could have done something like names car and then like minus 86. This would kind of give us the same thing. But this is like safer because this is explicitly removing that purchase variable from the list of variables. So xcols are all of the columns we kind of want to consider in our modeling effort here. Once again, we're going to do we're going to set the seed because we do need to do some random sampling type stuff, right? So you always want to set the seed when you're doing that. And we're going to break our data up into two groups, training and testing. And we're using that initial split function once again from the R sample package, right? So here you can see train one has 4,075 observations. Test one has 1747. That's going to get us to the 5,822. We don't mess around with this test set. It sort of goes off to the side, right? That's going to be our final test, our final evaluation of model building. But so for this KKNN thing, we do need, like, it does take, rather than data frames, and this kind of gets a little bit to like the utility of some of those model packages I was talking about earlier. There's a whole suite of packages called tidy models that kind of like make a lot of this stuff easier. So since we're not using it, we kind of got to do it the hard way. So we got to know that that KKNN package doesn't take a data frame, it takes a matrix. So that's kind of a pain in the butt. That's one of the things that kind of make you know, you kind of have to know quite a bit about these modeling packages to leverage them. So it's a downside of not using that more complicated approach here. So we're going to create these matrices, right? So all this is saying is take this data frame, only select the X column. So like throw out the purchase, so the other 85 columns, and then make it into a matrix, right? And since these things, there's no missing data in here, and there's no, and everything's a number, so it's going to work. So if I were to just look at xtrain raw, right, this is now a matrix of values, right? So this thing is just it's different than a data frame because everything in here is a numeric value. And then our y, so these are our x's. Remember we said like the predictors or the independent variables are called x's lots of times. So this is our x's. And the thing we're trying to predict is going to be our y variables. And since this is a single column, numeric column, this thing ends up being a factor, right? No and yes, right? So I can look at y train, a bunch of no's and yeses. But since this is sort of stored as a factor variable, this thing actually is interpreted as numeric sort of behind the scenes. So we don't have to worry too much about that. So one thing we got to do is all of our centering and scaling, right? So here we can calculate for each column, right? We can calculate the mean of each column. And then we can also calculate the standard deviation of each column. So we are going to sort of get a little bit tricky here. We're using the supply function, but this thing is just going to calculate. Here's for each column, this is the mean, and then SDV is similarly the standard deviation of each column. And then I can use those values to scale the columns, right? So here I'm going to scale my training data and my testing data, right? But here you can see on my scaling my testing data, I'm using the mean and standard deviation that I calculated on the training data. That's kind of that sort of like thing we were talking about in the slides about we don't want to have leakage from the test data into our training thing. We kind of want to treat this thing as sacred. So in this case, we're doing everything on the up and up. We're centering and scaling the metrics, the statistics we calculated from the training data, and we're applying that to both the training data and the testing data. And then we we bring this back into a data frame, right? And then we can we're actually creating our grid of Ks that we want to sort of look at. And here we can uh, um, okay, so here, this is the grid we're going to evaluate. So we'll evaluate the 1 nearest neighbor, 3 nearest neighbors, 11 nearest neighbors, 51 nearest neighbors, 101 nearest neighbors. And I'll just kind of go through what goes on in this loop, but you kind of get the idea of loops here. We're going to go for each value of K, we're going to, okay, so if we said like J is 1, so now we can say like K is 1, because that's the first K that we care about. And we will fit a K nearest neighbors model. Right, so this it looks kind of similar to what we were doing with the GLM, right? We have a formula. In these formula syntax, right, the dot means all of the variables, right? So we're going to train on, we're going to train and test on the same data. So we fit a K nearest neighbor model, and we want to get that probability out of there. And we will append that probability. So like scored train, right? So and we'll calculate a training AUC for our for that 1 nearest neighbor, right? So we're going to do this. We'll then take the model we sort of fit, and we'll apply it. Well, we'll actually refit the model, but we'll have that test data set this is an input to that KKNN algorithm. We will calculate our p-hats, and we will sort of assign a test AUC. So what we'll do here is we'll have 2 vectors of performance. The model performance that we would see on if we just did the in-sample performance on the training data. And then this takes a little bit of time. Okay. Okay, so this is sort of the point of all this, right? When we evaluate for K-nearest neighbors, the model performance in sample, which is what we did. So this is the AUC of the model when we look at the training data set, right? Everything looks pretty rosy, right? In fact, like we actually see a bit of degradation as we go down as we get higher Ks, because this is taking the average result of a lot of neighbors, right? So it looks like it does really well for low numbers of K and less good for higher numbers of K. But all of these evaluations look very rosy, right, in sample. But this is sort of the trick here, is because like when we take that same model and apply it to our test data set, or this is actually like our out of sample data set, we see a sort of a different story. Like this model does really well in this algorithm does really well in sample, but less good at a sample. So like this is an algorithm that is susceptible to overfitting, and that's kind of what we're sort of trying to do. So let's sort of use cross-fold validation to help us try to see if we can pick a value of K, right? So in this case, we're going to really expand, and I'm cheating a little bit because I kind of did some work to see what values of k would kind of work here. But we're going to expand our grid. We're going to consider like high numbers of k, a lot of neighbors here. So we're going to redo our seed setting. And we're going to like do the same algorithm for the most part, where we fit a model, right? So this is the same thing we were doing up top, but now we're applying it to our training and validation sets that we get from our folds within our cross validation. Right, so we're going to create a 10-fold cross validation here. We're going to consider a bigger grid of Ks, right? But we'll store these things in a matrix, right? So each row is a fold, and the columns are the K values. And what we're going to do is, I'm not going to step through this code here, but we're basically going to, you can see that I've got like, I'm going to step through all of the folds, and then for each fold, I'm going to evaluate each value of K to see what the sort of the performance is within what the model performance at a sample cross-validated model performance is for each value of K within the fold. So this is going to take a little bit of time because I kind of have a loop within a loop, right? But it doesn't take that long. We can kind of wait around for this thing to execute. Might take like upwards of a minute. But you know, if you kind of go through this code, it's doing the same thing I just did in the previous loop, for loop, except I've inserted like a sub loop, so it's got a nested loop. I'm going across all the values of K, and I'm doing it for each fold within my 10-fold cross validation. So like, you know, how many what did I call that thing? K grid. So like, right, so it's I'm evaluating performance across 12 different values of K. My grid of Ks is of size 12, and I've got 10 folds. So like, I I essentially fit 120 models here. So that's the idea with cross validation. You end up fitting a lot of models. That's why that loop took so much time. But here I can summarize this data, and I could see here that like you know, it turns out that I need quite a few neighbors here to get us a solidly performing out of sample model performance. But it does come back down, right? So there is some sweet spot out here around 1,200 neighbors, right? But you can see like for one neighbor, I was looking at 541. And then sort of my performance steadily started increasing, getting better and better as I got more neighbors. And I sort of arrived at like like the best performing choice for K. So this is sort of the idea of like hyperparameter tuning, right? Like we're going to use cross-fold validation to help us sort of pick a good value of K, right? So my best K ended up being 1,201. And then once again, so once we used cross-validation to help us pick that value of K, right, then I would fit a new model with all of my training data, and I would evaluate it on that holdout test data that we sort of took at the beginning. Right, so here I'm going to pick that 1201. I'm going to run a k-nearest neighbors model, and I got a performance of 688, which was not quite as good as this 724, but you know, is a good choice of K. So I know that was a lot, and it was a little bit more on the sort of programming side of things with the with the for loops and whatnot, right? So what we just did and why it felt like a lot of work, right? We ran vfold cross validation by hand. So typically you would try not to do that by hand. We created the fold, we scaled inside each fold so we had no leakage. We repeatedly fit the model and we scored each fold and summarized the results. So that's a lot of moving parts, but it's on purpose so that you can kind of see what's happening in there, right? In real projects, this gets repetitive fast, right? Pre-processing inside resampling, repeated fitting and scoring, keeping everything organized, avoiding subtle leakage bugs. So people use workflows that automate the plumbing. And this is what I was talking about with tidy models. So we're not really going to get too deep into tidy models. So tonight's lecture was mostly about like the concepts that we sort of employ with sort of cross validation and resampling and hyperparameter tooling. So like we used a small piece of it. So R sample and yardstick are components of this tidy models uh, ecosystem. But there's other pieces to help us with pre-processing, that model interface faces stuff, parameter tuning, end-to-end workflows, and eventually like, productionalization of models and whatnot. Um, so if we did lean more into this framework, we could sort of apply pre-processing inside the flows automatically, tune hyperparameters without writing loops, keep results in consistent structure, and reduce the chance of leakage. But it's like a whole thing, right? So I don't want to kind of throw a lot of new vocab and object types uh, on your plate and any sort of different workflow style. So in this, for part one of this two-part course that Professor Hayes and I do, uh, we're prioritizing more of the ideas and the base R type of stuff. But if you do want to explore more, right, you can sort of search up getting started with tidy models, and then you'll sort of focus on these supporting packages. Like I said, we already did R sample and yardstick, but you've got sort of other packages in there. All right, so just to wrap up tonight, it's getting kind of late. Big takeaways from tonight is K nearest neighbors is an algorithm that's very simple, but is very dependent on the features. But that choice of K is a hyperparameter, and we can use cross-validation to help us pick a good value of K. And cross-validation helps us sort of have a view of the performance of the model on out of sample data, which is kind of the important thing, because we're really worried about overfitting. If you're going to use K nearest neighbors, you got to make sure you center and scale. And then there's a whole toolbox of feature engineering, which we just lightly touched on tonight, but just be aware that like things like centering and scaling for certain algorithms are mandatory. All right, so I think that was a lot, but we got through it, everyone. Hopefully, it's been really weird. It seems like every Tuesday we get a big, I mean, this wasn't even a big snowstorm. I don't know why they closed all the campuses, but hopefully next week we'll be able to meet up in person, and we'll do one more lecture before spring break, and then I'll hand over the reins to Professor Hayes, and you can get to we're doing like the blocking and tackling, the basic stuff, but you'll get to some more interesting stuff with Professor Hayes. So I hope you all have a good week, and fingers crossed, I'll see you all next week.
Thank you, Professor.
All right, thank you. Have a good evening. I'll talk to you. I'll see you next week. Bye.